Hello, this is Mengjia Yan, and today I will present attack directories, not caches, side-channel attacks in a non-inclusive world. This is work done with my collaborator Reid Spreebury, Barkov Gobi Reddy, and Professor Chris Fletcher, Professor Roy Campbell, and my advisor Josep Prilas at IEEE. Basically, we designed a new cache-based side-channel attacks targeting the latest Intel processor with a new cache hierarchy. And our attack does not require SMT. It works with the attacker and the victim on different cores, and does not require page sharing. And I'm from the computer architecture community, so from a computer architect's perspective, to be fair, this Intel processor design is quite reasonable in terms of performance, hardware complexity, and cost. So our attack is not targeting a specific bug. It's actually targeting the problem root in the feature of the cache is shared. And let's start. We all know that cache-based side-channel attacks are very popular and effective. For example, given a multi-core processor in the cloud, we have different virtual machines from different users. Even though we have software isolation, information can still leak via the shared cache resources. And these attacks has been demonstrated on cloud, a lot of public cloud, containers, and people write JavaScript code to do the attack, launch it on a mobile device. And the attack is very effective to steal keys, secret keys, monitor keystrokes from user, and monitor the browser content. And also we know that when the side-channel attacks work with speculative meltdown and all the other variations of speculative execution attacks, they can break memory isolation and dump kernel content and do many powerful things. So given the attacks are so popular and effective, why we need another cache-based side-channel attacks? The answer is these attacks, most of them do not work on the latest Intel processor. Let me show you. So we have many different attack techniques. Most of them come with this A+B format. Generally, when I look into these attacks, I classify them into two categories. The first category uses a special instruction called CLFlush. And the other category, where I highlighted some here, we call them conflict-based attacks because they do not need the CLFlush instruction. They use cache conflicts to perform the attack. These attacks are more stealthy and more difficult to defend against. And these attacks have only been demonstrated on inclusive cache hierarchies, which is fine because all the past Intel processors use inclusive cache, but things changed in 2017. In 2017, Intel released their new processor. The code name is Skylake X and Skylake SP. This processor comes with non-inclusive cache hierarchy. Then people think cache attacks will fail on these processors. And even now, if you search online, you can find articles such as, with a title such as, New Intel CPU Cache Architecture Boosts Protection Against Side-Channel Attacks. Well, this is when you need our new cache-based side-channel attack because our attack challenged this assumption and proved this is wrong. And we propose the first two cache attacks, conflict-based cache attacks, which work on the non-inclusive cache hierarchy. Before I give you all the details about the attacks, let me just give you some brief background about what's the difference between inclusive caches and non-inclusive caches. Modern caches are organized into multiple levels, generally have 3 levels in Intel processors. Here I show a private L2 cache and shared lasso cache. In an inclusive cache, all the L2 lines will be duplicated in the lasso cache, like this. And this will happen to all the L2 lines. So here, the lasso cache is inclusive of the L2. It is the superset of L2 lines. Well, in a non-inclusive cache, this may not be the case. Basically, a private L2 line may or may not duplicate in the lasso cache. And according to our evaluation, we find all the exclusive line means it is not shared line, will never duplicate in the lasso cache. Attacks will be very different on these two different types of cache hierarchies. How can it be different? Let me show you a very classical prime probe attack. Left, I have the inclusive cache, and on the right, I have the non-inclusive cache. When the victim accesses a target address in an inclusive cache, the line will be inserted into both the L2 and the lasso cache because the cache is inclusive. Then, when the attacker wants to evict this target address out of the cache, the attacker will access a bunch of addresses mapped to the same cache set in the lasso cache. Once it accesses enough addresses, it will create a lasso cache conflict. This conflict will evict the target address out of the lasso cache, and as a result, the corresponding L2 copy of the line will also be evicted because the cache wants to maintain the inclusive property. And we call this line inclusion victim because the line is evicted due to the inclusive property, not because of any local conflicts. And this is very important for modern cache attacks. Modern cache attacks is so powerful so that the private cache is transparent to the attacker. So given a single cache line address, attacker can monitor all the victim's accesses on it. But things will not be like this on a non-inclusive cache, because to begin with, when the victim accesses target address, the line will not be duplicated in the lasso cache. And after this, no matter how many lines attacker accesses, even attacker takes the whole lasso cache, it can still not create cache conflicts, and no inclusion victims can be created. Therefore, without the capability to evicting the victim's line, attacker loses the visibility into the victim's private cache. That's why conflict-based attacks are very difficult on non-inclusive caches, and that's why people believe it will fail. But as I mentioned, we make it work. We make it work by not exploiting cache conflicts. We exploit conflicts on the directory structure. The directory structure here is not the software directory in the operating system you use to understand. This is actually a hardware structure. And it also has another name called smooth filter. It is structured is used to track the presence information for all the cache lines in the cache hierarchy. It can be in many different formats. A very classical format is a bit vector. Given 8 cores, then a direct entry can have a bit vector with a length of 8. And each bit indicates whether the corresponding core's private cache has the copy of the line or not. And you can learn this from any advanced computer architecture course. And luckily, since I'm a computer architecture student, so I know this beforehand. The things I do not understand is how this directory is specifically organized in the latest Intel Skylake S processor. And this is what we reverse engineered by doing a lot of experiments. In the paper, we provide very detailed documentation about how we reverse engineer this structure step by step. But today, due to the time limit, I will just show you our reverse engineering result. Here is a slice of the shared lasso cache. As we all know, it has data cache lines inside organized into ways and sets. We find there are 2 extra structures inside. The first one is called traditional directory, TD for short. This traditional directory holds directory entries for all the cache lines in that particular slice. So it is a one-to-one mapping of the cache line array and the traditional directory. So the traditional directory has the same number of sets and ways as the cache line arrays. There's another structure called extended directory. This is the directory that holds the directory entries for all the cache lines in the L2, but not in the lasso cache. A very important thing here is that the directory is inclusive, because you need to keep track of the presence information for all the cache lines in the whole cache hierarchy. Otherwise, it is useless, right? So in this sense, because the directory is inclusive, it is our new attack surface where we launch our cache-based side-channel attack. And I just want to mention that. So this is structure for this non-inclusive cache. In an inclusive cache, you also have directory, which you do not really see. You only have the traditional directory because that is enough to hold all the cache lines, but you cannot see it. And when people attack the inclusive cache, they are also attacking the directory because it's a one-to-one mapping. Okay, so now I will visualize how a prime probe attack works on a non-inclusive cache. So the first step we do in prime probe is prime. And instead of exploiting cache conflicts, we exploit conflicts in the extended directory to enforce the victim's line to be evicted from L2 to lasso cache. And this is the system we work with. we have the victim and attacker on different cores. They share the loss of cache. I only show one slice of it. And I will use green block to indicate target address and the red block to indicate attacker's addresses. And I use solid block to show the cache line and the slashed block to show the corresponding directory entries. First, the victim accesses line. The hardware will insert the line into the L2, and the corresponding entry will be in the extended directory. When the attacker wants to evict this line, it will access a group of addresses mapped to the same ED set, extended directory set, as the target address. Once it filled up that set, it creates ED conflict, and the ED conflict will evict this line to be migrated from ED to TD. And as I had mentioned before, all the TD entry has one-to-one mapping to the cache line array in the lasso cache. So you need to have a cache line in the lasso cache. And this will enforce the eviction of the victim's line to migrate from the private L2 to the lasso cache. And this is the inclusion victim. And you can see the prime approach, the prime step is completed. Now let's see how the probe works. As we all know, the probe is just to re-access all the addresses used in the prime step. And if victim does nothing in the between, when the attacker re-accesses all the addresses, it will see all L2 hits, very short latency. But if the victim re-accesses the line will go back to the L2. And this will be observed by the attacker. How can it work? When the line goes back to L2, it will make the TD entry migrate to the ED. Now you have another ED conflict. So the hardware needs to do a swap here. So attacker's entry will be migrated to the TD. And this operation enforces one of attacker's line to be evicted from the L2. And when the attacker measures the latency, it will see an L2 miss instead of all L2 hits, so longer latency. By just comparing the time difference, attacker will figure out whether the victim have accessed the address or not. So you do all the same thing as what you did in the prime probe. The only difference is that we exploit the directory conflicts, and the attacker needs to figure out the mapping between the directory and the physical address it used in the attack. Now I will demonstrate this attack on a very simple victim, and just want to show you how effective this attack is and how noiseless this attack is. I will use this very simple example. It's the square and the multiply explanation computation, and it's not really interesting, but it's widely understood and easy to explain. In this particular example, the loop iterates over each key bit, and it performs a square mod operation each iteration. And if the corresponding bit is 1, it will further perform a multiply operation. And in this particular example, I use the multiply function as the target address, and we will use prime probe to monitor it. And this is the trace we get. You can see it's very clear. The x-axis is the epoch ID. We use 500 cycles as epoch ID. And if the victim does not access any line, the attacker will see all L2 hits. It will take only 100 to 175 cycles. And if the victim accesses a single line, the attacker will see around 225 cycles. It's very easy to be distinguished whether the victim accessed or not. And here, I already marked a block 0, which means the victim is doing a square operation without accessing the multiply function. And the bit 1 is a square operation followed by the multiplication computation. And the attacker just needs to look into this trace and iterate each bit of it. Very clear, without any complicated post-process technique. And this is what I will cover, but there are many more interesting things in the paper. So as we all know, if you want to target the lasso cache and do the prime probe attack, you need an eviction set. And the eviction set construction algorithm, the old eviction set construction algorithm, does not really work for non-inclusive cache hierarchy, so we proposed our new version of it. And this is in the paper. Also, we documented the detailed step of how we reverse engineer the directory structure and all the parameters and configurations and the special operations within this structure. A lot of details. And also, in addition to prime probe attack, we also designed a multi-threaded high bandwidth evict and reload attack, which is slightly different from prime probe because the directory handles shared cache line differently from the private cache lines. And we also show attack results on AMD machines. The short summary is that our attack does not work on AMD machines because they have very small number of cores on each chiplet, so probably they do not use directory, but their design is not scalable from the perspective of a computer architect. And I've attended this conference for more than 1.5 days, and I see a common question asked during the Q&A session is, what's the future, whether you have countermeasures of it. So we did think about it. There are two simple solutions. One is increase the directory associativity. If you have enough associativity and you can hold all the cache lines in your L2, then you will not have directory conflicts. But from a computer architect's perspective, it is not realistic to build. You will never build a set associative array with more than 100 ways, just too expensive and very low performance. Another possible solution is to do the way partition of the directory just as what we did with the cache. But it's not really feasible because the extended directory only has 12 ways, which means you can support as maximally 12 security domains. But these server processors, they can have up to 28 cores. So they can potentially have 28 security domains. So this way partition is not really feasible when you have many different security domains. So since this work is completed early last year, we do have some solution for that. This paper is SecDir, a secure directory to defeat directory side channel attacks from our group. This work is published in ISCA, International Symposium of Computer Architecture this year, and will be presented next month. For people who are not familiar with this conference, it is the top conference in the computer architecture community. And we are the people who try to design and propose different hardware designs, and we are the person who try to collaborate with security people to come up with better designs. And if you are interested, you can check out this paper. To summarize, in this paper, we reverse engineered the directory structure, and we proposed the first two cache attacks work on the non-inclusive Intel Skylake X processor, and we evaluate it on the RSA encryption algorithm. To summarize, we think the directory is the unified structure for conflict-based cache attacks because when you attack inclusive cache, you are also attacking the directory. That's it. Thank you, and I'm ready for questions.
Questions?
Hi, Brian Maskenberg, Western Digital. The example algorithm that you were attacking has very clear side channels. It has a timing side channel in the pseudocode. It's also not regular with respect to memory accesses. Is there a way to use this against algorithms that are regular in their timing and memory access pattern, or is that a sufficient countermeasure for cryptographic algorithms?
So clearly, using our technique, you can give us a cache address, and we can monitor the victim's accesses on that cache address. So our attack is just a technique that as long as the victim, its access pattern leaks some secret information, we can do with that. It's very general.
So if we were to only use cryptographic implementations that had regular memory access patterns.
You mean the access pattern does not leak any secret information? Yes, of course, we cannot work with that.
Okay.
Yes.
Thank you.
Sorry, did you try attacking other types of targets besides the one you described in the
Yeah, we
talk?
only show this one because, so as you can understand that, it's a very general technique to monitor the victim's accesses, right? As long as you can monitor the accesses, and if the access leak information, you can break it.
So basically anywhere prime plus probe is good in terms of targets.
Yes, it's very precise and effective.
Great. Any other questions? Okay, let's thank the speaker again.